Good afternoon, everyone. How are you all? Am I audible to you? Okay. So, in the last two I will say lectures, what we have done, we have understood few concept of magnetic field, like what is magnetic field, and after that we have calculated magnetic field through various using Biot-Savart law. I will say for a straight wire, for a circular loop, for a arc, and we have seen some variation, some special cases of straight wire. We have solved some questions there. Now, in this lecture, what we are going to do, our aim should be to complete Ampere's law, one another way to find the magnetic field, and very useful method to find the magnetic field of a certain symmetric bodies. So, on that note, let's start our session. Okay. So, first of all, before starting the Ampere's law, we will start with the magnetic field due to a circular loop at the axis. In the previous class, what we have seen, the magnetic field at the center of the loop. Now we are going to study the magnetic field at the axis of the loop. So before starting that, I just want to tell you one more term. So this is the main topic. I am just telling you one more thing. What is magnetic moment? That what is magnetic moment? So just remember this term before moving further. What it says, for example, let's suppose this is a loop which has some radius, let's suppose r. Here, this is the radius. Just focus on the loop, not on this distance x. Focus on the loop. And this loop has some current I. Clear? Then its magnetic moment is defined as, is denoted by M. Its magnetic moment is denoted by M and is known as I into A. This magnetic moment is a vector quantity and it has the same direction as we associate with the area vector. Now, my task is to explain you the direction as well. So, right now, just remember the formula. What is magnetic moment? The formula of magnetic moment for a loop. Magnetic moment of what? Of a loop is I into A, where I is the current in the loop, A is the area of the loop, and magnetic moment is a vector quantity. Very good. Direction, what will be its direction? So answer is direction is same as the direction of area vector. Now I will tell you how to get these directions. So just listen to me very carefully. Now one more thing that may be possible is that if the loop has some turns and it is a coil of n turns, that means what if I say for a coil of n turns, like if the coil has some turns, then magnetic moment becomes, you will multiply with the n number of turns, Ia remains the same. So magnetic moment will become NIA. Now, after doing this, remembering the formula, area of the circular loop is pi r square. You can easily know that area, if loop is not circular, it is square loop, then side square is the area. If it is a rectangle, length into width. So it may be of any shape. I'm not talking about only circular loop. You can take any sort of loop, but it should be a loop. Loop means it starts and finishes at the same point. For that, magnetic moment is I into it is a vector quantity. Now direction. The method to find the direction is similar to what we have used for the magnetic field. Just take your right hand and curl the fingers in the direction of current. Like in this loop, you can see that the dotted portion of the loop is inside the plane and solid portion is outside the plane. So current is coming from inside to outside like this. You can see my hand. Current is coming like this. So you need to curl your right hand fingers in the same way, and you will find that this direction thumb indicates right side. According to my frame of reference, thumb indicates right side. So what is the direction? You will say right side. For which loop? For this loop, magnetic moment is in the right direction. Clear? Now, one more thing. If I ask you the direction of one more situation for one more loop, I will say, let's suppose this is a loop. Let's suppose this is a loop. Can you imagine the plane of the loop? Can you imagine the plane of the loop? This loop is placed in the horizontal plane, like in the XZ plane. Like you can say, like suppose current is moving in this direction. This loop is placed in the XZ plane. Now, what will be the direction of the magnetic moment? You will again curl your right hand fingers. And how you will curl your right hand fingers? Just place your right hand and curl the fingers in the direction of current. And the thumb will again indicate in the upward direction. So, what is the direction of magnetic moment? You will say magnetic moment is in the upward direction, sir. Is it clear? Okay. I think these things are clear in your mind that how to find the direction of magnetic moment. Now, after knowing this thing, I am moving further for the main topic. What is the main topic? Magnetic field due to a circular loop at the axis. This is our main topic. So let's consider the loop has some current I, clear, and has a radius R. This is the axis of the loop. This is the axis of the loop, and at this point P, you want to calculate the magnetic field. So the relation, the derivation part I am not doing here, but what I am doing, I am writing the relation. So B is equals to, I am telling you the way you can write the relation, that is mu naught over 4 pi. This is the constant magnetic field. In magnetic field, you will always find this constant mu naught over 4 pi and 2m divided by r square plus x square raised to the power 3 by 2. This is the relation for the magnetic field wave. What is M here? You will say M is the magnetic moment. M is the magnetic moment. Is this clear? Okay, sir. Now, not always you will find this relation in the books because this M can be written as pi r square and you can simplify things there because M is what? Magnetic moment, which is known as I into A. So you can write M as what? I pi r square. So you can simplify things. Pi can be cancelled out. You can do a lot of things here. So that's what I am not focusing about. You should remember this relation 2m over r square plus x square raised to the power 3 by 2. Now again, one more thing I will tell you here. What if I say if loop is very small, if loop is very small, then what will happen? You will say r is very less than small. You can say r is smaller than the x. Loop is small as compared to what? Its radius is small as compared to the distance on the axis. So r is very small. So you can ignore the r in this term. So it will become what it will become? B is equals to mu naught over 4 pi 2m divided by x cube. Now, as soon as I see this relation, something clicks in my mind. Something striking in my mind. What is this? That I have studied this similar kind of formula in electrostats. You have studied that electric field at the axis of a dipole. What you have studied, electric field at the axis of the dipole. If you can recall, then I will tell you exact relation. I'm just asking you to recall what electric field at the axis of dipole. And if you can recall it, you will remember that the electric field at the axis of the dipole is Ke 2p over r cube, where r is the distance of the point from the center of the dipole. Can you resemble these things? This electric field is similar to what the magnetic field due to a circular loop. So after doing the comparison thing, you can conclude that a current carrying loop behaves as a dipole, not of electric dipole, but magnetic dipole. That means it must have two poles, north and south pole. This is a very basic conclusion that we can draw from this relation, and which is very important as well. What is the conclusion? Are you getting my point? What is the conclusion? That current carrying loop behaves as a magnetic dipole. And how we can draw this conclusion? By comparison. Is this clear? Okay, sir. This is very clear. Now, what is the direction of magnetic field? The same method will be used in the direction of for the direction of magnetic field that we have used for the direction of magnetic moment. Now, after this, one more conclusion I will say that for a loop, direction of magnetic field, direction of area vector, and direction of magnetic moment, all three will be same. Is this clear? Mark my words. Okay, moving further. Now, what are the punchlines that you can conclude from this? A current carrying loop behaves as a bar magnet. Bar magnet or nothing but it is also named as dipole, or you can say magnetic dipole. Magnetic dipole is nothing but bar magnet. Is this point clear? That means if I say this, like this is this is a dipole. This is a sorry, this is a current carrying loop placed in the horizontal plane. I can see that you can understand that what is the plane of the loop. This is something like this in the horizontal plane. Like you have taken one ring and placed it on your horizontal surface. So this is the loop and it has some current I. And if it is behaving as a bar magnet, then it must have some north pole and must have some south pole. Clear this point again. So it must have some north and south pole. So for that, what I say, the direction of magnetic moment. First of all, direction of magnetic moment you should find. So direction of magnetic moment, if I use the right hand rule, so direction of magnetic moment is something like that. This is the direction of magnetic moment. Now another point is that you should remember direction of magnetic moment is always from south pole to north pole. Direction of magnetic moment is always from south pole to north pole. That means this side of the loop is south pole and this side of the loop is north. Are you getting my point? We know that the direction of magnetic moment is always from south to north. So you can write this point as well. What I'm saying, the direction of magnetic moment is from south pole to north pole. And you know the south and north pole of the magnet has two poles. Now, if I ask you again one more similar kind of question, for example, you have one more loop like this. This loop is placed in the YZ plane. Which plane? YZ plane. Now, if I say you have some current in it like this, I. So what we have seen in the punchline, a current carrying loop behaves as a bar magnet. That means this loop must behave as a bar magnet and bar magnet must have north and south pole. So what will be the north pole and what will be the or where will be the south pole? So for that you should find the direction of magnetic moment first. Because if we know the direction of magnetic moment, we will know the south pole and north pole. So for that, what you should do, take your right hand and curl the right hand fingers in the direction of the current. Like in this loop, current is moving in this direction. It is going inside from outside, like this. So you should curl your right hand in such a way, in the same way. So if you do this, you will find your thumb in this direction. So you can mention here that magnetic moment for this loop is in this direction. According to my frame of reference, this is left side. So magnetic moment is in the left direction. So what will be the south pole and north pole? This is going to be south pole. This is going to be north pole. This is very useful concept when we go further for the next chapter EMI. Then you will find it very useful in that chapter, in that case as well. So I think this is clear. So one more question for your practice. You should answer while practicing. I'm giving you one more question. If this is a circular loop and it has some current I, this loop is placed in the XY plane. What you should do, you should find the south pole and north pole of this loop. Where is south pole and north pole of the loop? I think till now everything is clear in this concept. Moving further. Another punchline. If it is a bar magnet, what we have learned, it behaves as a bar magnet, then how its field lines will be? You can clearly say that its field lines should also be like a bar magnet that you have studied in class 10. So I will directly show you the field lines of a loop. This is a loop. These are going to be the field lines. Is this point clear to you? That how the magnetic field lines of a loop will look like? They will look like something this one. Clear? These lines, all of these lines will form closed loop. All of these lines will form closed loop, like this, everywhere. There will be closed loops. This line will get completed in this way, and it is going to be a closed loop. These lines are going from the loop, through the loop, or I will say, they are going through the loop like this, everywhere. Moving further. Now, I think every point is clear till now. Now we are moving further for the next topic, which is again a very important concept, that is Ampere's law. What it says, first of all, before definition thing, I will tell you one thing, that you have studied Gauss theorem in electrostats. Have you? So in electrostats, the Gauss theorem is used basically for the calculation of electric field. For some symmetrical bodies, like in your syllabus, if I talk about, you must have studied the field due to a long wire, the electric field due to a long wire, the electric field due to a long sheet, the electric field due to a spherical shell, due to a solid sphere, due to a cylinder, or you might have learned as well. So now what I'm saying, in the same way, Ampere's law is something, it is kind of a tool which can be used to find the magnetic field due to some certain symmetrical bodies. So what is the statement of Ampere's law? I will say, before reading to the definition, what I will say, you can see here, for example, let's suppose there is a wire. There is a straight wire, long wire, which has some current I. And from previous study, like from the first lecture, I think you will know that this wire will create a magnetic field in the circular form, in the form of the loops. So what you should do there, you know that the magnetic field of a straight wire is symmetrical. Symmetrical in this way, like it is something like that, in the form of circular loop. It is in the form of circular loops. These circular loops are in the XZ plane. Is this point clear? Say at least something. So this field is in the circular shape and this is symmetrical field. So in such situations, you can use the Ampere's law to find the magnetic field very easily. So what is the statement I will say? The statement says that integral B dot dl, or you can say closed line integral B dot dl is equals to mu naught times current enclosed by the loop. Now I will tell you once again. In the Gauss theorem, you have some imaginary surface. In the Ampere's law, you have some imaginary loop. You will have some imaginary loop. And what is the statement? The integral or closed line integral B dot dl. I will explain. Don't go with the terms like what is closed line integral, what is this B dot dl. We are studying it for the first time. So I will explain you word by word. I will explain how to use these things. So statement says the closed line integral B dot dl is equals to mu naught times current inside the loop. Current inside the loop. Now, one thing from this discussion that you should know that we have to choose some some loop actually. So how to choose the loop? This is the big question. How to choose the loop? This is the big question, and this loop is known as Amperian loop. Now, I will explain you that how you can choose the loop so that it is very beneficial for you. First of all, it must be symmetrical with the field. It must be symmetrical with the field. Now, what this point means, for example, I have shown you a straight wire. The magnetic field of this straight wire is, you can say, in this form of circular loops. So the loop that you will choose should also be circular in shape. So are you getting my point? If field is circular in nature, then your loop must also be circular in nature, circular in shape, or you can say. Is this point clear? Now, another thing, what if, sir, field is uniform? How uniform field is made? You can say, sir, uniform field is made something like that. This is the shape of some uniform field, which is equidistant parallel lines. Then how can I make such a loop? For circular loops, you told me, sir, just draw this loop in this form of circular loop. Now, in this case, how you can draw the loop? Can you see that? This is the format of the loop that you can draw. The thing is, it must be symmetrical with the field, means that more of the point or most of the points must have uniform field. Must have uniform field. Is this point clear? This is how we choose the loop. One thing, it should be symmetrical in the form of shape. Another thing, it must contain lot of points which have uniform field. Now, second point, it must pass through the point where you want to calculate magnetic field, where magnetic field is asked. I think these 2 points are clear. One more thing that I will tell you here, that is, after selecting the shape of the loop, you should provide it a sense of rotation. You should provide it a sense of rotation, and this sense of rotation may be anything from clockwise to anti-clockwise. Like in this loop, you can say, I can provide it some sense of rotation. I can provide it some sense of rotation. One thing, choose the Ampere loop. Second thing, associate it with some direction. It might be clockwise, it might be anti-clockwise. It all depends on you. What is the benefit of deciding the sense of rotation? I will tell you in the next part, on the next slide. Is this clear till now? Moving further. Okay. Now, on this slide, I will tell you what is the purpose of deciding the sense of rotation. Purpose of sense of rotation. Listen to me. Now, let's suppose there is a loop. Just look at me. There is a loop of, if I change the color of the pen, let's suppose this is the loop. I hope you can imagine this loop the way I am drawing it. This loop is in the, or I will draw it more precisely so that it look like more like a loop. So this is the loop placed in the horizontal plane. Now, let's suppose there are two wires which are passing through this. One wire is this one, another wire is this one. These two wires are passing through the loop, and one has a current I1, another has a current I2. Clear? Now, what we need to do from the previous slide, you should know, we want to calculate current inside the loop. We want to calculate the current inside the loop. Now, coming back to the topic, current inside, there are two currents. One is I1 and one is I2. Both have different directions. So, it might be possible that it is I1 minus I2, or it might be possible it is I2 minus I1. But which is more accurate, which is correct? Actually, we don't know. We can't say it is, someone might, sorry, someone might tell you, sir, just subtract smaller values from the larger value. No, it's not true. So for that, sense of rotation comes into the picture. What is the purpose? Let's give it a sense of rotation. The question posed to you is clear. Now, after knowing the question, the solution is that just put a sense of rotation. Now, after putting the sense of rotation, you will see that just take your right hand and curl the fingers of your right hand in the direction of the current, in the direction of sense of rotation. If you curl your fingers, then thumb is going upward. And if thumb is going upward, then this upward direction will be considered positive and downward will automatically become negative. So for this purpose, I will say you can easily tell me that current enclosed inside the loop will be upward is positive, downward is negative. That is I1 minus I2. Now you can ask me if you have any doubt in deciding the positive side. What is the purpose of sense of rotation? To provide the positive side of the current. Nothing else. Nothing more than that. To provide the positive sense, positive direction of the current. I think this is clear till now. If I ask you one more thing, if you can comment here. If I ask you, like, suppose this is a loop and two wires are going through it. One has a current I1, another has a current I2. Clear? Or I will say the direction, let's change the direction. Let's suppose this is I2. Then I am saying that this is the direction of sense of rotation. So what will be the value of I enclosed? Can anyone answer? What will be the value of I enclosed? Is it I1 minus I2 or it is I2 minus I1? What will be the value? How you can decide it? If this is the direction of sense of rotation, what you should do? First of all, you should know what is loop. Loop is in the YZ plane. If loop is in the YZ plane, the dotted portion I have drawn the dotted portion that is into the plane, that is inside the plane of your paper. So current or the sense of rotation is something like this. So you need to turn your right hand in this way and the thumb is in the right side. So what is the positive side? This right side is positive. And if right side is positive, you will say, sir, right side is positive. That means I1 is going to be positive and I2 is going to be negative. This is the way you can calculate I enclosed. Okay. Is it clear? You can use your chat box to comment so that I can understand that you are listening to something. After moving, after understanding this basic thing, okay, let me just confirm one thing. Have you completed this chapter? Have you completed or started this chapter in your classes? Okay, moving further. Now there is a checkpoint for you. Checkpoint means some questions will be there for you, which are very fundamental and concept related questions. Okay. So there is three loops. I will say there are three loops, L1, L2, and L3. There are three loops, and you can see there are total four currents, I1, I2, I3, and I4, and loop has some sense of rotation which is mentioned in the question. What is your task? To find the value of I enclosed for each loop. For each loop, I am asking, for example, let's start with the first loop that is L1. For L1, you need to tell me where is L1? Sir, this is L1. This red color loop is L1. So you want to tell me, you need to tell me what is the value of I enclosed for L1. I enclosed will be whether it is I1 minus I2, I1, I2, I3, I4, what will be? Two currents are passing through this L1. Clear? Which direction of current is positive? I will say, using my right hand, I can clearly say that what you should do. First of all, you should identify the loop. This loop is placed horizontal in this direction. Current is moving from outside to inside like this. If you can see it clearly, then if I take my right hand and curl my fingers in the same way, thumb will be in the upward direction. And if thumb is in the upward direction, then this side is positive for L1 loop. Similarly, for L2 loop, this side is positive. And for L3 loop, this side is again positive. So I have decided the positive side of each loop. Actually, the question must contain some different kind of arrows for each loop. Okay, no problem. This is the question that we need to follow. So for L1, I will say I1 is positive and I2 is negative. So that will be I1 minus I2. Clear? Now again, if I say for L2, L2 is where this is L2. It contains three currents. One, two, three. So which is positive? I1 and I4 are positive. I2 is negative. So I will say I enclosed will be I1 is positive, I4 is positive, and I2 is negative. Clear? I have drawn, I have written some I capital. You can draw it in the small I. Again, another loop is loop 3. This is loop 3. What is I enclosed? You can say, sir, there is no current passing through this loop. No current is inside the loop. That means for I3, you can clearly say that I enclosed will be 0. I think all these three things are clear to you. This is the basic checkpoint for you before moving further. Now I am moving further for the main topic. Using Ampere's law, we need to calculate magnetic field due to a hollow current carrying wire. Now, how the hollow current carrying wire will look like? This is the hollow current carrying wire. This is long. That means it has some infinite length this side and has some infinite length this side as well. And it has some current. What is current? It has some current, something like that, I. And this current, if this is hollow wire, this current is on the circumference of the cylindrical wire. I think this point is still clear to you. Moving further, first step was to choose the Amperian loop. Now, what we have seen that for a long wire, the current, if long wire has some current, the magnetic field will be circular. So my loop is also going to be circular in nature. So what I can say, let's take a Amperian loop. So first situation I will say, if point is outside the wire, what is the meaning? We want to calculate the magnetic field. If I want to calculate the magnetic field, we have to decide at which point I'm just wanting to calculate. So it might be a point which is outside, it might be a point which is at the circumference, and it might be a point which is inside. So there are three possibilities at which we want to calculate field. So right now I am saying if point is outside the wire, that means point is something like that. So for that, one thing that you should do, just draw a Amperian loop. I am drawing a Amperian loop like this one. Can you imagine this loop? This loop is something in the XZ plane. And after selecting the loop, let's suppose this is the axis of the wire and radius of the wire is r, and this distance is small r. This distance is small r. That means from the axis, the distance of the point P is small r. Now we can provide some sense of rotation. I am providing it some sense of rotation like this. Suppose this is the sense of rotation we have provided to the loop. As soon as I provide sense of rotation, you will know that the direction of current which is positive is upward direction. Current is how much? I in the loop. Okay. Now, what Ampere's law states that closed line integral of B dot dl is equals to mu naught times current enclosed. B is the magnetic field. If you can see that this loop is at equal distance from the wire, that means magnetic field will be constant. So I can take this outside the integration, and what will remain integral dl, that will be mu naught times I enclosed. Now in the next step, what is the value of integral dl? Integral dl, if you add these dl parts, these small dls, you will get the circumference. And what is the circumference of the circular part is 2 pi r is equals to mu naught. And how much current is inside the loop? This is the loop and it has total I current inside the loop, that is I. So B is equals to mu naught I divided by 2 pi r. Mu naught I divided by 2 pi r. This is our final result that we have drawn, we have derived using Biot-Savart law by taking almost 1.5 pages. It can be derived using Ampere's law using just one or two statements, one or two lines. Is this point clear to everyone? So from this conclusion or from this result, you can draw a conclusion that magnetic field is inversely proportional to the distance. That means if you move further from the, you move farther from the wire, from the uh, current carrying wire, the magnetic field will decrease and the relation will be B is reciprocal to R. Clear? Now, moving further. What if point is inside the wire? What if the point is inside the wire? Now, I am saying second case, if point is inside the wire. Okay. So before moving further, I just need one confirmation from your side, from all of you. It's two confirmation that I want. One thing, that am I audible to you, everyone? Second thing, have you studied this chapter before, or you are just starting this chapter right now? So these two confirmations I want from your side, and I am just watching the messages. If you can send any. Okay, let's suppose this is the axis of the wire. Okay, the point is inside the wire. This is the point where I want to calculate the magnetic field. So your first step is to draw the Amperian loop. Draw the Amperian loop. You can draw the Amperian loop something like that, and you can associate some direction with it. This loop is completely inside the wire, or completely inside the cylindrical wire, I will say. So if this loop is completely inside the cylindrical wire, what you can do, you can again write closed line integral B dot dl is equals to mu naught times current enclosed by the loop. Now in this whole part, you will see that current enclosed by the loop is zero, because all the current is on the circumference of the loop, on the wire. So current inside the loop is zero. So this term will become zero. So if this term is zero, so B is zero. That means field inside the loop, inside the wire, inside the hollow wire is zero. This is the punchline that you can draw. Field inside the hollow wire is zero. Is this clear to you? Okay. Moving further. So right now we have studied Ampere's law and its application to find the magnetic field due to a hollow current carrying wire. Now we can extend our knowledge to apply the same for the solid current carrying wire. If wire is solid, then what will happen? Let's see at the next slide. Fuel due to a long solid current carrying wire. So how this solid wire will look like? It will look like something this one. This is solid, and this whole wire has some current. Let's suppose it has some current I. It has some current I. And this current is uniformly distributed inside it. This current is uniformly distributed inside it. Clear? Now, again the same question. What are the 3 points at the outside point, circumference, and inside? So let's take first case. If point is outside. Outside what? The wire. Clear? So I will draw a Amperian loop there. associate a sense of rotation with it. Now just apply Ampere's law. What it will do if I apply Ampere's law, what is the statement you should remember? Integral B dot dl is equals to mu naught times I enclosed. Again, wire the loop is at the equal distance from the wire. That means B is constant. Integral dl is again 2 pi r. What is r? R is the radius and r is the distance of the or the radius of the circular loop. Is equals to mu naught times, you can tell me what is the current enclosed by the loop. This loop encloses the complete wire. So all the current I is passing through the loop. So what is the total current passing through the loop is I. So what is the value of B? Magnetic field will become mu naught I over 2 pi r. Can you see that this magnetic field is similar for the hollow wire as well? Hollow wire has also the same magnetic field at any point outside it. So again, you can conclude that B is reciprocal to R. Just remember these conclusions. These are very important. Okay. Now, after remembering this conclusion and remembering one more point that for hollow wire, for solid wire, magnetic field outside any point is same. Oh, there comes another point. There comes another point if point is outside. If point is inside the wire, point is inside the wire. Let's take some point which is inside the wire. Let's suppose this is the point. This is the axis, and this is the point where you want to calculate the field. Is the red color visible? Or I can take another pen. Let's suppose I think blue will be more visible. So this is no, blue is not going to be visible. Okay, okay, okay. I think this one will be visible. Yeah. So this is our Amperian loop, and I have associated a sense of rotation with it. This loop is completely inside. What is the radius of the loop? This is the radius, which is small r. What is the radius of this wire? Is capital R, which is already known. Radius of the wire is what? Capital R. Now, your task is to again apply Ampere's law. And if I do it with quickly, I am just writing the statement integral B dot dl is equals to mu naught times I enclosed. Now, again, B is constant taking outside. Integral dl is nothing but 2 pi r. This is the circumference is equals to mu naught times. Now I will stop. That what is the value of current inside the wire? Because total current is I. Total current passing through the wire is I. This I current is distributed uniformly in the wire. Now, what will be the current passing through this small? This area is small. If total current is I through the whole wire, then this small portion will have some smaller current. Then we need to calculate that smaller current. So I will tell you that how you can calculate this value of a small current. So just look at here. Look at this portion. I am making a certain box there so that you can understand. Okay. I enclosed. Is it visible? Will be, or I can say, have you studied current electricity? Just tell me. I think you have studied the chapter current electricity in which you know the current density term. I think you have studied that current density part. So J into dA. You know that current density is I over A. You know that na J is equals to I over A. So I will be J into A. So now what I am saying, J is the current density, dA is the small area through which you want to calculate the current. So this is the small area we want to calculate the current through which. So what you can write, I enclosed is equals to J is current density. Current density means current, that is total current I divided by area of the loop is pi r square. This is the current density of the wire. Total current is I, total area is pi r square. This cross section area is pi r square into the area through which I want to calculate the current is pi small r. You can cancel out pi here. So that will become I into small r square by capital R. You can, after putting this value, I can cancel out this small r with the power. So what will be the value of magnetic field? This magnetic field will become B is equals to mu naught over 2 pi. This 2 pi can be brought here. I small r over capital R square. And you can close this as a standard box. What is more conclusive here is that magnetic field inside the loop, inside the wire, is directly proportional to the distance. Is directly proportional to the distance, irrespective it is indirectly or inversely proportional to the distance outside. So, are you getting my point? Now, after this conclusion, I am on the stage of drawing some graphs. What kind of graphs I can draw? Variation of field with distance for for wire, or you can say straight wire. Okay, these are mostly asked questions in your exam, in your NEET and in your mains exam. So what I say, first of all, I will draw for hollow wire. For hollow wire. What is the conclusion for hollow wire? Magnetic field inside is zero and magnetic field outside is directly proportional, is inversely proportional to R. Clear? And for solid wire, magnetic field inside is directly proportional to R and magnetic field outside is inversely proportional to R. By knowing these data, I can draw a graph between magnetic field like this magnetic field, and suppose this is our distance R. Magnetic field and distance R, and distance R is taken from where? From the axis of the wire. You know that. This is the axis point, 0. Now you can draw the graph. B inside is 0. Inside means up to radius. I can change the pen color like this. Field is 0. Very good. Up to what distance? Up to this point, which has a point R is equals to R. Up to radius. Magnetic field is 0. And suddenly, magnetic field increases. And after outside, it starts decreasing. It's a reciprocal graph, something like that. This is the graph of hollow wire, magnetic field versus R. Now, how this graph will look like for solid wire? Magnetic field versus R. Can anyone draw this graph by yourself? Whenever I say magnetic field is directly proportional to R, how this graph will look like? How this graph will look like? Y is proportional to X. This is a graph of a straight line passing through the origin. So this graph will look like something straight line, something like that. Up to what point graph follows this trend? The graph follows this trend up to the circumference. And after circumference, that is outside, it becomes reciprocal to R. And reciprocal to R means it becomes something like that. Is this point clear to you? I hope this is clear to everyone. On this note, I will say just try to remember these things. And I have completed three. This is the third lecture of this magnetism chapter. Before that, we have completed two more lectures on that. So if you want to understand things from the beginning, you can watch those two lectures. Those two lectures were the base. If you can watch those two lectures, you can ask, and you will find a link for that. Actually, I will say, and just watch and note, take a note of those two lectures. On that note, I am just ending the session here. So goodbye, everyone. Be regular, be punctual, and you will learn new things daily. So on this note, I am just ending the session. Bye, everyone.